March 17, 1943, Rechlin Experimental Airfield, Germany. Oberingenieur Fritz Nallinger's hand trembled slightly as he opened the aluminum cowling on the B-17's No. 3 engine, exposing the turbocharger installation that had confounded German engineers for 3 months. "The Americans cannot possibly manufacture this complexity on an industrial scale," he wrote in his technical evaluation. "No nation could machine such precision components while simultaneously fighting a global war." Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. Through the maze of exhaust ducting and intercooler plumbing, Nallinger studied the General Electric B-2 turbocharger that powered this bomber to altitudes where German fighters gasped for oxygen. The turbine wheels spun at 21,000 revolutions per minute, driven by exhaust gases that would melt inferior steel in minutes. High-temperature alloys using cobalt and chromium, materials Germany could barely obtain, transformed waste heat into additional power exactly when it was needed most, at altitudes approaching 35,000 feet. In German hands, this captured fortress, nicknamed Wulf Hound, represented more than an intelligence prize. It represented a technological chasm German industry could not bridge despite 4 years of effort. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Nallinger and his team would discover in the weeks ahead would prove more devastating to German confidence than any tactical defeat. The turbocharger wasn't merely superior engineering, it was the visible manifestation of American industrial advantages so profound that German planners quietly acknowledged the strategic implications. Understanding how America achieved altitude supremacy meant understanding why Germany had already lost the technological war. The journey from mystery to revelation had begun 3 months earlier on December 12, 1942. Lieutenant Flickinger piloted B-17F serial number 41-24585 during a bombing run against the Luftwaffe servicing facilities at Romilly-sur-Seine in occupied France. His aircraft, part of the 360th Bombardment Squadron of the 303rd Bombardment Group stationed at RAF Molesworth in Huntingdonshire, England, carried the unofficial name Wulf Hound painted on its nose by American ground crew. The mission started routinely, but German fighters had other plans. Messerschmitt Bf 109s and Focke-Wulf 190s attacked the American formation with aggressive persistence. Machine gun and cannon fire tore through Wulf Hound's fuselage and wings. One engine sputtered and died, another began trailing smoke. Flickinger faced an impossible choice as his crippled bomber fell behind the protective formation. Scanning the landscape below through breaks in smoke from his damaged engines, Flickinger spotted what appeared to be a suitable field near Melun, France, approximately 60 miles southeast of Paris. With remarkable skill considering his aircraft's damage, he brought the massive 30-ton bomber down for a wheels-up landing in a field. The B-17 slid across grass and mud, its ball turret ploughing a long furrow before coming to rest. The crew emerged with hands raised, expecting to become prisoners of war. What they didn't expect was how valuable their intact aircraft would become to German intelligence. Within hours, Luftwaffe ground crews and Wehrmacht soldiers swarmed over the captured fortress. Engineers photographed every system, every structural detail, every technological feature before the bomber could be damaged. The bomber represented an intelligence windfall beyond anything previously captured. Most downed Allied aircraft arrived in pieces, but Wulf Hound sat nearly intact, a complete example of American heavy bomber technology ready for exploitation. German recovery specialists immediately recognized the prize before them. This was the first B-17 flying fortress to fall into Luftwaffe hands in flyable condition. The capture represented an unprecedented opportunity to understand not just American bomber design, but the technological philosophy that made such aircraft possible. German technicians worked quickly to transport the damaged but repairable bomber to Leeuwarden Airfield in the Netherlands. 2 days after capture on December 14, 1942, German mechanics completed temporary repairs. German national insignia replaced American markings. Large black crosses adorned the wings. A swastika marked the tail. Two Messerschmitt Bf 1-10 heavy fighters took position as escorts, and a hand-picked German crew climbed aboard for the ferry flight to Rechlin, the Luftwaffe's premier testing center located approximately 50 miles north of Berlin. Despite clear German markings and advance notification to every Luftwaffe fighter base and flak battery along the route, some German forces fired on their own captured prize, inflicting minor additional damage before recognition signals could be confirmed. The incident highlighted both German eagerness to destroy American bombers and the difficulty of coordinating operations across fractured command structures in a military organization beginning to feel the strain of fighting on multiple fronts. When Wulf Hound touched down at Rechlin, it entered a world dedicated to understanding enemy technology. Rechlin served as the central testing facility for all Luftwaffe aircraft evaluation, the German equivalent to Wright Field in Ohio or the Royal Aircraft Establishment at Farnborough. Every captured Allied airplane that could be repaired to flying condition eventually made its way to this secretive base. Here, German engineers dissected foreign technology, searching for weaknesses to exploit and innovations to copy or counter. For 3 months following its arrival in mid-December 1942, Wulf Hound remained grounded while teams of specialists conducted exhaustive examination. Engineers removed panels to study structural design, marveling at sophisticated stressed skin construction. They measured skin thickness, analyzed alloy composition, tested rivet patterns. Every system received detailed documentation. The electrical network revealed American approaches to systems integration. Hydraulic controls showed sophisticated valve designs. The oxygen distribution system demonstrated understanding of high-altitude operations. But it was the engine installation that captured the most intense scrutiny. The 4 Wright R1820 Cyclone engines were themselves unremarkable, 9-cylinder radials producing 1,200 horsepower each at takeoff. German, BMW, and Daimler-Benz engines matched or exceeded this output. What made these American engines extraordinary was what surrounded them: a maze of exhaust ducting, turbine housings, intercoolers, and control systems that transformed adequate power plants into high-altitude performers. Each engine mounted a General Electric turbocharger installation beneath the nacelle. Exhaust gases from the 9 cylinders collected in a manifold, then rushed through heavily insulated ducting to the turbine housing. Inside that housing, a wheel machined from high-temperature steel alloy spun at 21,300 revolutions per minute, driven by the kinetic energy of exhaust gases, leaving the engine at over 1,000 degrees Fahrenheit. This turbine wheel connected through a common shaft to a centrifugal compressor on the opposite side of the housing. As the turbine spun, the compressor forced ambient air into the engine's supercharger at pressures far exceeding what the engine-driven supercharger could achieve alone. The system created a 2-stage compression process. First, the turbocharger compressed incoming air. Then, the engine's own mechanical supercharger provided final compression before the air-fuel mixture entered the cylinders. The brilliance of this arrangement became apparent when German engineers analyzed performance at various altitudes. At sea level, the turbocharger contributed little. The engine's own supercharger provided adequate air pressure. But as the bomber climbed through 15,000, 20,000, 25,000 feet, atmospheric pressure dropped dramatically. Without the turbocharger, the engine would lose power rapidly as air became thinner. The turbocharger compensated automatically. As atmospheric pressure decreased, the pressure differential between the turbine inlet and outlet increased. This greater differential meant more energy available to drive the turbine faster. Faster turbine rotation meant higher compressor output, maintaining manifold pressure despite thin air outside. The system became more effective exactly when it was needed most, a self-regulating solution to high-altitude power loss. At 25,000 feet, where German fighters struggled to maintain combat power, the B-17's Wright Cyclones delivered nearly full-rated output. At 30,000 feet, where most German aircraft could barely maintain level flight, the Fortress still produced enough power for formation flying and evasive maneuvers. The service ceiling exceeded 35,000 feet with full combat load, an altitude that placed the bomber beyond the effective reach of most German defenses. Luftwaffe aeronautical engineers quickly grasped the tactical implications. American bombers could fly above the optimum altitude for German anti-aircraft artillery. Flak effectiveness decreased dramatically above 25,000 feet due to reduced projectile velocity and longer time of flight. Fighter interception became more difficult as German pilots struggled with reduced engine performance and control authority in thin air. The altitude advantage provided by turbocharging created a defensive zone where American bombers operated with relative impunity. But understanding the tactical advantage was different from replicating the technology. When German engineers disassembled the General Electric B-2 turbocharger for detailed examination, they discovered engineering that seemed simple in principle, but proved devastatingly complex in execution. The turbine wheel, approximately 10 inches in diameter, was machined from a single forging of high-temperature steel alloy. The blades, integral with the wheel rather than attached separately, curved in precise aerodynamic profiles designed to extract maximum energy from exhaust gases. The alloy itself presented the first major obstacle. American engineers used stellite alloys containing substantial percentages of cobalt, chromium, and tungsten. These exotic metals provided the combination of strength, hardness, and oxidation resistance necessary to survive prolonged exposure to exhaust gases exceeding 1,000 degrees Fahrenheit. Germany possessed neither adequate supplies of these metals nor the industrial capacity to produce them in the quantities required for mass production. Cobalt, essential for high-temperature applications, came primarily from deposits in the Belgian Congo, now under Allied control. Germany's limited cobalt reserves were already allocated to other critical applications, including cutting tools for machine shops and permanent magnets for electrical equipment. Chromium supplies, while slightly better, remained inadequate for expanding production of specialized alloys. The turbocharger demanded materials Germany simply could not obtain in wartime. Even if materials could be secured, manufacturing presented equally daunting challenges. The turbine wheel required precision machining to tolerances measured in thousandths of an inch. Any imbalance would cause catastrophic vibration at 21,000 revolutions per minute. The bearings supporting the turbine shaft operated at extreme temperatures while rotating at speeds that generated enormous centrifugal forces. American engineers used specialized high-temperature bearing alloys and sophisticated lubrication systems that German industry had not developed to production readiness. The control systems added another layer of complexity. The B-17 featured an electronic turbocharger regulator manufactured by Minneapolis Honeywell, a sophisticated electromechanical device that automatically adjusted turbine speed to maintain desired manifold pressure. As the bomber climbed, the regulator sensed decreasing atmospheric pressure and opened waste gates that allowed more exhaust gas to bypass the turbine, preventing overboost that could damage the engine. As the bomber descended, the regulator closed the waste gates, increasing turbine speed to maintain power. This automatic regulation freed pilots from constant manual adjustment while preventing potentially catastrophic overboost conditions. German turbocharger experiments, limited as they were, required manual control by flight engineers who monitored multiple gauges and adjusted settings continuously. The Minneapolis Honeywell system demonstrated American expertise in electronic controls and automatic regulation that German industry had not matched. On March 17, 1943, Wulf Hound finally took to German skies for its first flight under Luftwaffe control. Flugkapitän Hans-Werner Lerche, an experienced test pilot selected for his skill and engineering background, conducted the maiden flight from Rechlin. The bomber handled smoothly, responding to control inputs with surprising docility for such a large aircraft. Over subsequent weeks, multiple German pilots flew Wulf Hound in varied test profiles, designed to explore every aspect of performance and handling characteristics. High-altitude evaluations confirmed American claims about operating ceilings above 30,000 feet. Engine performance tests documented power output at various altitudes, revealing how the turbocharger maintained manifold pressure well into the stratosphere. Formation flying exercises demonstrated stability that explained how Americans maintained those tight defensive box formations that Luftwaffe fighters found so difficult to penetrate. But it was the systematic disassembly and analysis of the turbocharger system that provided the most sobering lessons. Fritz Nallinger, chief of power plant development at Daimler-Benz, led a team of specialists who documented every component, every dimension, every material specification. Their classified report, completed in late April 1943, painted a picture of technological sophistication that far exceeded German capabilities. The report began with technical specifications: turbine diameter, blade angles, housing design, bearing types, all meticulously measured and photographed. Then came materials analysis. Spectroscopic examination revealed alloy compositions rich in elements Germany lacked. Metallurgical testing showed heat treatment processes that produced material properties German foundries struggled to replicate. Manufacturing analysis identified precision machining techniques and quality control standards that required industrial infrastructure Germany did not possess at scale. The conclusions section made uncomfortable reading for German military leadership. First, Germany could not produce equivalent turbochargers in operationally significant numbers before 1945 at the earliest, if ever. The materials shortages alone made large-scale production impossible. Even if cobalt and chromium could be obtained through increased trade with neutral nations or synthetic substitutes developed, the manufacturing expertise required to produce reliable turbochargers at the necessary quality levels would take years to develop. Second, attempting to retrofit existing German bombers with turbochargers would require extensive redesign. The complex ducting, the intercooler installations, the control systems, all demanded integration from the initial design phase. Adding turbochargers to aircraft designed without them would reduce performance, increase weight, and create maintenance nightmares. The B-17 had been designed from the outset around turbocharged engines. German bombers had not. Third, and perhaps most devastating, the turbocharger represented only one aspect of American technological advantages. The report noted sophisticated propeller governors, advanced intercooler designs, electronic control systems, and manufacturing quality that collectively demonstrated industrial capabilities Germany could not match. If America could produce such complex systems for every bomber, while simultaneously building fighters, tanks, ships, and transport aircraft, what hope did Germany have of matching such output? Intelligence assessments following the Rechlin evaluation reached similar conclusions through different analysis. If one captured bomber showed this level of technological sophistication, how many could American industry produce? The numbers, when German intelligence analysts ran calculations based on known American industrial capacity, suggested production rates that seemed impossible yet proved conservative. Boeing's Seattle plant alone could build 12 B-17 seconds per day at peak production, more bombers in a month than Germany's entire heavy bomber program produced in a year. General der Luftwaffe Erhard Milch, State Secretary for the Luftwaffe and one of Germany's most senior aviation administrators, examined Wulf Hound personally during a visit to Rechlin in late March 1943. His reaction, recorded in meeting minutes later captured by Allied forces, revealed the psychological impact of confronting American technological superiority. After climbing through the bomber and examining the engine installations, Milch reportedly told subordinates that Germany faced enemies who possessed not just more resources, but fundamentally different approaches to industrial production and technological development. The turbocharger exemplified this difference. American engineers had identified high-altitude performance as a critical requirement for strategic bombing in the 1930s, then systematically developed the technology needed to meet that requirement. General Electric, working with Army Air Corps funding, spent over a decade perfecting turbocharger technology before the war began. By 1939, when Germany invaded Poland, American turbocharger technology had matured to production readiness. Germany, by contrast, had pursued different priorities. Luftwaffe doctrine emphasized medium bombers optimized for close air support of ground forces, rather than strategic bombing deep into enemy territory. High-altitude performance received less emphasis because the missions envisioned did not require it. When circumstances changed and strategic bombing became necessary, Germany lacked both the technology and the industrial capacity to develop equivalent systems quickly. Daimler-Benz and Junkers had experimented with turbocharged variants of their engines. The DB622, DB623, and DB624 projects all attempted to mate turbochargers with existing engines. None progressed beyond experimental status before being abandoned due to materials shortages, reliability problems, and limited tactical benefit given the missions German bombers typically flew. These cancellations occurred in 1942 and 1943, exactly when American turbocharger production reached industrial scale. The contrast could not have been starker. While American engineers refined and mass-produced proven turbocharger technology, German engineers abandoned development programs that might have provided similar capabilities had they received adequate priority and resources. The decisions made in the 1930s about doctrinal priorities and technological development now manifested as insurmountable disadvantages in 1943. Hans-Werner Lurch, who would become the most experienced test pilot of captured Allied aircraft during the war, flew Wulf Hound extensively during spring and summer 1943. His post-war memoir, published decades later under the title Luftwaffe Test Pilot, Flying Captured Allied Aircraft of World War II, provided detailed accounts of his experiences with the bomber. Lurch approached captured aircraft with scientific curiosity rather than ideological prejudice, a professional attitude that made him invaluable to the Luftwaffe's evaluation program. In his memoir, Lurch devoted particular attention to the B-17's engine installation. The B-17 interested us so much because of its flying characteristics, he wrote, but more because of its supercharged engine, which gave excellent performance at higher altitudes. These superchargers were activated by exhaust-driven turbines, which became really efficient, corresponding to the greater difference in air pressure at higher altitudes, exactly when more power was needed. For that reason, the Flying Fortress was primarily made available to the power plant experts, who tried to get to the bottom of as many details of the engines as possible. Lurch described how German engineers transformed the captured bomber into a flying laboratory. The most varied measuring instruments were installed for this purpose, he continued, so that the fuselage behind the bomb bay was like a laboratory with engineers in attendance. These engineers monitored turbine speeds, manifold pressures, exhaust gas temperatures, intercooler efficiency, and dozens of other parameters across multiple flights at various altitudes. The data they collected painted a comprehensive picture of how the turbocharger system performed under operational conditions. What emerged from these exhaustive tests was understanding without the ability to replicate. German engineers now knew precisely how American turbochargers worked, what materials they required, what manufacturing precision they demanded, what control systems they employed. But this knowledge could not create cobalt deposits where none existed. It could not build precision machining capacity that required years to develop. It could not overcome the fundamental resource and industrial limitations that constrained German technology. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The psychological transformation occurred gradually through spring and summer 1943 as the implications became inescapable. Germany was not fighting an enemy with slightly better technology that could be countered through tactical innovation. Germany was fighting an enemy whose industrial capacity and technological sophistication operated on a different scale entirely. The turbocharger wasn't merely a superior component, it was evidence of systematic American advantages across multiple domains. Materials access favored America. While Germany scrambled for cobalt and chromium, American industry drew from global supply chains protected by Allied naval supremacy. Nickel from Canada, tungsten from China, chromium from South Africa, cobalt from the Belgian Congo, all flowed to American factories in quantities German planners could only imagine. The oceans that isolated America from direct attack also connected it to resources worldwide. Manufacturing expertise favored America. Decades of mass production experience, beginning with Henry Ford's assembly lines, had created industrial know-how that German craftsman-based traditions could not quickly match. American factories standardized components, used interchangeable parts, employed semi-skilled workers with specialized jigs and fixtures. German factories still relied heavily on skilled craftsmen hand-fitting complex components, a slower and more labor-intensive approach that could not achieve American production rates. Engineering philosophy favored America. American designers prioritized reliability and maintainability over maximum performance. The B-17's turbocharger could be removed and replaced by ground crews in the field within hours. German experimental turbochargers, when they functioned at all, required extensive maintenance by specialist technicians. American systems were designed for operational use by average personnel. German systems often assumed highly trained specialists would be available. Most fundamentally, strategic vision favored America. American military planners in the 1930s correctly identified strategic bombing as a future requirement and invested accordingly in enabling technologies like turbochargers, bomb sights, and defensive armament. German planners focused on different priorities appropriate for the wars they expected to fight. When circumstances demanded capabilities Germany had not developed, catching up proved impossible within wartime constraints. The examination of Wulf Hound's turbocharger installation triggered broader strategic assessments within German military leadership during summer 1943. Admiral Karl Dönitz, newly appointed commander-in-chief of the entire Kriegsmarine while retaining control of U-boat operations, received briefings on the Rechlin findings. The parallels to his own technological crisis were unmistakable. Just as American bombers operated at altitudes where German defenses struggled, Allied aircraft and ships hunted U-boats using centimetric radar that German warning receivers could not detect. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The pattern repeated across multiple domains. In radar technology, cavity magnetrons gave Allies detection capabilities Germany could not match. In computing, American and British advances in fire control and bombing calculations exceeded German capabilities. In signals intelligence, Allied code-breaking penetrated German communications, while Enigma's supposed security proved illusory. In nuclear physics, though neither side yet knew the other's progress, American resources dwarfed German efforts. Each technological advantage traced back to similar root causes: Allied access to global resources, superior industrial capacity, different engineering philosophies, and strategic investments made years before the war began. The turbocharger exemplified this pattern. America had committed to high-altitude bombing in the 1930s, then developed and mass-produced the enabling technology. Germany had made different choices based on different strategic assumptions. Now, in 1943, those choices constrained options in ways that could not be quickly remedied. Field Marshal Erhard Milch convened crisis meetings throughout spring 1943 to address Germany's deteriorating technological position. The Rechlin evaluation of captured Allied aircraft, particularly the B-17, provided evidence that could not be dismissed as defeatism or enemy propaganda. Physical hardware demonstrated Allied capabilities conclusively. German engineers who examined these aircraft were among the Reich's most qualified technical experts. Their assessments carried weight that intelligence reports alone could not achieve. Milch pushed for accelerated development of German high-altitude aircraft. The Fokker-Wulf TAR-152 program, designed around the Junkers Jumo 213 engine, received increased priority. But even this promising design faced insurmountable obstacles. The Jumo 213, while powerful, lacked turbocharging. It relied instead on a mechanically driven two-stage supercharger that added complexity, weight, and reduced reliability compared to simpler single-stage designs. Performance at extreme altitude remained inferior to turbocharged American engines, despite the added complexity. Alternative engine programs fared no better. The Daimler-Benz DB622 project, which would have paired a two-stage mechanical supercharger with a turbocharger on the DB603 engine, was abandoned in January 1943 due to materials shortages and development difficulties. The DB623, featuring twin turbochargers, suffered the same fate. The DB624, with both mechanical and turbocharging, was cancelled in April 1943. Each cancellation removed potential solutions to Germany's high-altitude performance deficit. The reasons for these cancellations revealed systemic problems beyond any single program. Cobalt shortages made producing turbine wheels at scale impossible. Chrome and nickel limitations affected high-temperature ducting and bearing materials. Manufacturing capacity, already stretched producing existing engine types, could not accommodate complex new designs without reducing output of proven models. Every attempt to develop turbocharged engines encountered the same material and industrial constraints that had doomed previous efforts. Even if materials and manufacturing could be resolved, time worked against Germany. American B-17 production reached peak rates in 1944, with Boeing alone building 362 bombers per month, 12 per day from a single facility. Douglas and Vega added thousands more from their production lines. By the time Germany could hypothetically field turbocharged engines in meaningful numbers, American production would have already placed thousands of high-altitude bombers over Europe. The mathematics were inexorable. Germany's entire four-engine bomber production for the war, including problematic Heinkel He-177, totaled approximately 1,100 aircraft across all variants. America built over 12,700 B-17 seconds alone, plus additional thousands of B-24 Liberators, B-29 Superfortresses, and other heavy bombers. The production differential exceeded 10-1 in America's favor, and that ratio would have been even more lopsided had Germany attempted to match American technological sophistication. Throughout summer 1943, Wulf Hound continued its service at Rechlin as engineers conducted increasingly specialized tests. They evaluated single-engine operation with turbocharged engines to understand how pilots managed asymmetric thrust. They tested various fuel grades to determine if lower-octane German fuels could substitute for the 100-octane gasoline American engines required. They measured cooling system performance to understand how intercoolers managed temperatures in the compressed air charge. Each test revealed additional aspects of American engineering philosophy. The B-17 demonstrated remarkable redundancy. Multiple electrical systems meant single failures rarely proved catastrophic. Self-sealing fuel tanks, while known to German engineers, were implemented more comprehensively than in German aircraft. The oxygen system provided adequate supply for prolonged high-altitude operations. Every design decision prioritized operational effectiveness and crew survivability over minimizing weight or complexity. German bomber design followed different principles. Weight reduction received higher priority because German engines produced less power than American counterparts at equivalent displacement. Complexity was avoided because German doctrine assumed shorter missions with better ground support. Redundancy was limited because resources were scarce, and every kilogram saved allowed additional bombs or fuel. These design choices made sense within German strategic assumptions, but created aircraft less capable than American bombers in prolonged high-altitude operations. On June 12, 1943, Wulf Hound appeared at an exhibition held at Leyrs Airfield for Luftwaffe commanders and technical specialists. Alongside the captured B-17 sat examples of other Allied aircraft that had fallen into German hands. A B-24 Liberator heavy bomber showed American approaches to long-range bombing from a different design perspective. A P-47 Thunderbolt fighter demonstrated American fighter design philosophy, emphasizing ruggedness and firepower over agility. A P-51 Mustang revealed the threat posed by long-range escort fighters. Multiple British types, including Lancaster, Mosquito, Typhoon, and various Spitfire variants, illustrated Allied technological diversity. The display served multiple purposes beyond simple aircraft recognition training. It demonstrated captured technology that German engineers might adapt or counter, and it provided sobering evidence of Allied industrial capacity and technical sophistication that was beginning to outpace German development in numerous areas. Luftwaffe officers who attended the exhibition came away deeply troubled by what they saw. One participant later wrote that the contrast between German and American manufacturing quality became immediately apparent even to casual observers. American aircraft components fit together with precision tolerances that German craftsmen admired. Matching construction quality across thousands of aircraft indicated sophisticated quality control systems. Smooth finishes reflected attention to aerodynamic detail. Careful assembly showed systematic production methods rather than improvisation driven by resource shortages. German aircraft produced increasingly with slave labor under constant Allied bombing showed rough workmanship, mismatched panels requiring hand-fitting, and improvised repairs using non-standard materials. The visual comparison alone conveyed messages about relative, industrial capacity that no amount of propaganda could obscure. When frontline pilots and commanders could personally examine American bombers and see the quality of construction, their confidence in German industrial superiority eroded rapidly. After its appearance at the Lehr's exhibition, Wulf Hound returned to Rechlin for additional testing before eventual transfer to Kampfgeschwader 200 for operational service in September 1943. This specialized Luftwaffe unit conducted clandestine operations, including agent insertion, supply drops to isolated German forces, and long-range reconnaissance. The B-17's range exceeding 2,000 miles and high-altitude capability made it ideal for missions requiring penetration of Allied-controlled airspace. Flying captured American bombers deep into Allied territory offered unique advantages. At night or in poor visibility, Allied radar operators might mistake the German crewed fortress for a friendly bomber returning from operations, allowing the intruder to penetrate defenses undetected. Even in daylight, a B-17 flying at high altitude could potentially join American formations temporarily, gathering intelligence on tactics and procedures. The deception could buy precious time before Allied defenses reacted. But operating captured aircraft demanded resources Germany could barely spare. Every gallon of fuel burned testing enemy bombers was fuel unavailable for combat operations. Every skilled mechanic maintaining non-standard aircraft was a mechanic unavailable for maintaining operational German types. The intelligence gained from studying captured technology, while valuable, could not overcome the fundamental limitations that prevented Germany from matching Allied capabilities. Hans-Werner Lerche flew other captured B-17 seconds that arrived at Rechlin after Wulf Hound transferred to operational service. On October 9, 1943, B-17F, serial number 42-30336, named Miss Nonnally II by its American crew, crash-landed near Varde in Denmark after developing engine trouble. The crew bailed out, but the pilot successfully brought the aircraft down intact, demonstrating the B-17's docile handling even in emergencies. German recovery teams arrived quickly, and Lerche himself flew the bomber from the field to Esbjerg airfield, then on to Rechlin for evaluation. The fact that Lerche could fly an unfamiliar American bomber out of a farm field with no instruction manual, no checkout flight, and no ground training spoke volumes about both his exceptional skill and the B-17's forgiving flight characteristics. The bomber received the German code 7+8 and served in evaluation roles until at least December 1944. Each newly captured fortress provided fresh opportunities for examination. Engineers compared different production blocks, looking for evolutionary changes that might indicate vulnerabilities to exploit or improvements requiring new German countermeasures. They tested various German ammunition types against B-17 structure to determine optimal attack profiles for fighter pilots. They evaluated the effectiveness of different German cannon calibers, finding that 20mm weapons were marginally effective, while 30mm cannons proved devastating when hits were achieved. What emerged from these exhaustive tests was a comprehensive picture of an aircraft representing peak American bomber development in 1943, and a level of technological integration that fundamentally altered strategic bombing calculus. The turbocharger installation was merely the most visible aspect of a complete system designed to deliver heavy bomb loads to distant targets, despite determined opposition. Consider the complete picture German test pilots documented at Rechlin. 4 Wright Cyclone engines, each producing 1,200 horsepower, provided 4,800 total horsepower, driving the bomber to speeds approaching 300 miles per hour at altitude. 4 General Electric turbochargers maintained sea-level manifold pressure to 30,000 feet and beyond. Minneapolis Honeywell electronic controls automatically regulated turbine speed across the entire flight envelope. Sophisticated intercooler installations managed compressed air temperatures. Multiple redundant systems ensured single failures rarely proved catastrophic. The defensive armament that had so impressed German evaluators when first examining crashed B-17 seconds in late 1942 now made more sense in context. 1350 caliber machine guns on the B-17G model weren't merely heavy firepower. They represented the defensive component of a comprehensive system, enabling daylight strategic bombing. The altitude advantage provided by turbocharging placed bombers above most anti-aircraft effectiveness. The heavy defensive armament deterred fighter attacks. The rugged construction absorbed battle damage. The long range delivered bombs to targets deep in enemy territory. American strategic bombing doctrine, developed in the 1930s and refined through painful combat experience in 1942 and 1943, it relied on this integration of multiple technologies. Precision bombing using the Norden bombsight required stable high-altitude platforms. High-altitude flight required turbocharged engines. Daylight operations required heavy defensive armament. Long-range missions required large fuel capacity and efficient engines. Each requirement drove specific technological development that collectively created capabilities Germany had not matched. German bomber development had followed different paths based on different assumptions. The Heinkel He-177, Germany's only operational four-engine heavy bomber, represented an alternative approach to strategic bombing. Powered by coupled DB610 engines, essentially two DB605 engines geared together, the He-177 achieved respectable performance in some areas but suffered chronic reliability problems. Engine fires caused by the unusual coupled engine design plagued the type throughout its service life. More critically, the He-177 lacked turbocharging. Its engines used mechanically driven superchargers that limited high-altitude performance compared to turbocharged American bombers. Service ceiling reached approximately 26,000 feet, adequate for many missions but inferior to the B-17's capability. The design emphasized other priorities, including dive bombing capability, a requirement that added weight and complexity while providing limited operational benefit given the missions actually flown. Total He-177 production barely exceeded 1,100 aircraft between 1942 and 1945. Many units refused to accept the type due to reliability concerns, preferring twin-engine medium bombers despite inferior range and bomb load. Germany simply could not produce four-engine heavy bombers in quantities approaching American output, and those produced suffered from design compromises that limited effectiveness compared to Allied types. The comparison extended beyond raw numbers to fundamental approaches. American bomber development prioritized operational effectiveness, accepting increased complexity and weight to achieve mission objectives. German development prioritized efficiency and simplicity, attempting to achieve adequate performance with minimal resources. These different approaches reflected different industrial capabilities and strategic circumstances. America could afford complexity because its industrial base could manufacture and maintain sophisticated systems. Germany could not afford such complexity because resource constraints demanded simpler solutions. When Luftwaffe pilots learned production statistics through intelligence briefings, morale suffered among thoughtful individuals who understood implications. What purpose did risking life to shoot down one fortress serve when 10 more would replace it within a week? The question haunted fighter squadrons as the strategic situation deteriorated through 1944. German fighters achieved remarkable tactical successes. Individual pilots became aces with dozens of bomber kills, but strategic outcomes remained unchanged. Every B-17 shot down over Europe represented tactical victory for the Luftwaffe pilot who achieved the kill. But within days, sometimes hours, another brand new fortress, fresh from Boeing's Seattle production lines, from Douglas plants in Long Beach, or from Vega facilities in Burbank, would replace the lost bomber, arriving in England with a fresh crew ready to continue the campaign. Boeing's Seattle plant alone produced nearly 7,000 B-17 seconds across all variants. Douglas contributed 3,000. Vega added 2,750. Peak production in 1944 saw Boeing building approximately 362 bombers per month, more than 12 per day from a single facility. German intelligence confirmed these figures through multiple sources, including aerial reconnaissance of English airfields, prisoner interrogations, and neutral country observers. The numbers seemed impossible yet proved conservative. American industrial capacity operated on scales German planners struggled to comprehend. Boeing's Seattle facility employed tens of thousands of workers on multiple shifts. Subcontractors across America manufactured components shipped to final assembly plants. The entire system operated with coordination and efficiency that represented decades of mass production experience. German factories still using traditional aircraft construction methods required weeks to build a single bomber. Skilled craftsmen hand-fitted components, manually riveted assemblies, individually adjusted systems. Quality was often excellent, but quantity remained limited by available skilled labor and traditional manufacturing approaches. American factories built bombers on moving assembly lines where semi-skilled workers installed standardized components using specialized jigs and fixtures. Quality was adequate, and quantity exceeded German output by orders of magnitude. The captured B-17 at Rechlin had taught Luftwaffe everything they needed to know about the Flying Fortress as a weapons system. They understood its strengths, including rugged construction, high-altitude performance, heavy defensive armament, and long range. They knew its weaknesses, including vulnerable nose area on early models, blind spots in defensive coverage, and relatively modest speed. They developed tactics that, when executed properly by skilled pilots, could destroy bombers despite their advantages. But this knowledge could not change fundamental arithmetic. For every German pilot who learned effective attack techniques, Americans trained 10 new bomber crews. For every fortress shot down over Germany, American factories built 5 replacement bombers. For every successful interception that disrupted a raid, a dozen more raids flew the next week with larger formations. The defensive firepower and altitude advantage provided by turbocharged engines represented only aspects of comprehensive systems designed to project American strategic power deep into enemy territory despite opposition. Luftwaffe General Adolf Galland, one of Germany's most successful fighter aces with 104 confirmed victories and eventual commander of German fighter forces, wrote extensively in post-war years about challenges defending against American daylight bombing. He acknowledged that individual German pilots often possessed superior training and combat experience compared to American bomber crews. German fighters, particularly late-war models, could outperform B-17 seconds in every performance metric. German cannons hit far harder than American .50 caliber machine guns. Yet, despite these advantages in equipment and pilot skill, German fighters could not stop the daylight bombing campaign that systematically destroyed German industrial capacity. Galland attributed this failure to multiple factors, but American industrial capacity topped his list of decisive elements. The Americans simply built more of everything faster than Germany could destroy it. The captured B-17 seconds proved this reality beyond doubt for German engineers who studied them. German engineers dismantled every system, evaluated every component, studied every design decision with thoroughness that would impress any technical investigator. They found much to admire in the bomber's design and little to criticize from pure engineering perspective. The fortress represented mature engineering executed with manufacturing excellence, integrating best available technologies into coherent weapons systems. But no amount of tactical innovation or pilot skill could compensate for material disparity in wars of attrition. Hans Werner Lerche flew numerous captured aircraft during his tenure at Rechlin, accumulating over 125 different aircraft types from various nations without a single serious accident damaging an aircraft or injuring the pilot. His post-war writing reflected professional respect for Allied aviation technology, tempered by frustration at German industry's inability to match Allied production rates and organizational efficiency. He flew B-17 seconds, B-24, Liberators, British Lancasters, Soviet bombers, and numerous fighter types from all combatant nations. Each aircraft taught specific lessons about Allied capabilities, but the B-17 remained strategically significant because it represented American strategic bombing doctrine made manifest in aluminum and steel. Every aspect of the fortress's design supported its mission to penetrate deep into enemy territory, deliver heavy bomb loads with precision, and return home, despite opposition. The turbocharger installation served as the critical enabler for this mission profile, providing altitude advantage that made daylight strategic bombing feasible despite heavy defenses. Without turbocharged engines maintaining power at extreme altitude, daylight strategic bombing would have proven impossible regardless of how many bombers America built. German fighters would have slaughtered formations flying at altitudes where they enjoyed performance advantage, forcing Americans to adopt night bombing like the British with reduced accuracy. The B-17's ability to fly above 25,000 feet transformed strategic bombing from theoretical concept to operational reality. By mid-1944, approximately 18 months after Wulf Hound's capture, the strategic bombing campaign had achieved decisive results. German industry lay in ruins across the Ruhr Valley and other industrial centers. Oil production facilities, systematically targeted from spring 1944 onward, could not meet military needs. Transportation networks collapsed under sustained interdiction bombing. Aircraft production, despite Herculean efforts to disperse factories and use underground facilities, could not replace combat losses. The fortresses had completed their mission despite heavy losses along the way. Nearly 5,000 B-17 seconds were lost to all causes during the war, including combat action, operational accidents, and weather. But American factories replaced losses faster than combat could inflict them, maintaining and expanding the bomber force despite attrition. The cumulative effect of hundreds of missions over 2 years systematically destroyed Germany's capacity to wage modern war. When Wulf Hound met its end during an American bombing raid on an airfield in April 1945, just days before Germany's surrender, the strategic bombing campaign had achieved its primary objectives. German industry could no longer support military operations. Fuel shortages grounded much of the Luftwaffe, despite having aircraft available. Transportation chaos prevented delivery of supplies to front lines where German armies faced defeat. The captured bomber that had taught Luftwaffe so much about American technological capabilities had become symbol of futility, fighting against overwhelming material advantage. The story of captured B-17 seconds in German service represents curious footnote to larger narrative of strategic bombing over Europe. These aircraft, built in American factories by American workers, flown by American crews on combat missions, shot down or forced down by German forces, then rebuilt and flown by German pilots, served as unique windows into Allied capabilities. They revealed strengths Luftwaffe needed to counter and weaknesses that could be exploited. They trained fighter pilots in attack procedures that saved lives. They supported special operations that achieved tactical objectives. Yet ultimately, they also demonstrated impossibility of Germany's strategic position by revealing scale of American industrial capacity. Every hour German technicians spent repairing captured American aircraft represented skilled labor diverted from maintaining German aircraft. Every gallon of fuel burned testing enemy bombers was fuel unavailable for combat operations. Every bullet fired during evaluation exercises represented ammunition Germany couldn't spare. Meanwhile, American factories produced more B-17 seconds every day, replacing losses faster than combat could inflict them. The turbocharger installation that so impressed German engineers represented not just superior component engineering, but comprehensive American advantages in materials access, manufacturing expertise, engineering philosophy, and strategic vision. Understanding how American turbochargers worked could not create cobalt deposits where none existed. It could not build precision machining capacity requiring years to develop. It could not overcome fundamental resource and industrial limitations constraining German technology throughout the war. The examination of one captured device in early 1943 had revealed truths German military leadership found difficult to accept but could not deny. America possessed industrial capabilities and technological sophistication operating on scales Germany could not match within wartime constraints. The altitude advantage provided by turbocharged engines was merely visible manifestation of deeper American strengths in industrial organization, resource allocation, and economic mobilization. No amount of tactical brilliance, pilot courage, or individual innovation could overcome such overwhelming disparity in industrial output. The mathematics were unforgiving. You cannot defeat an enemy who builds bombers faster than you can shoot them down, who trains crews faster than you can kill them, who delivers bombs in greater tonnage than your entire nation's industrial output across all sectors. The real secret weapon wasn't the General Electric turbocharger spinning at 21,000 revolutions per minute beneath the B-17's nacelles. It was the economic and industrial system that could design, manufacture, and deploy 12,731 of these bombers, while simultaneously building 300,000 aircraft of all types, 88,000 tanks, 41 billion rounds of ammunition, and everything else needed to fight global war on multiple fronts across several continents and 2 major oceans. No wonder German test pilots, after flying dozens of captured Allied aircraft and seeing firsthand the quality and quantity of enemy equipment, concluded that Germany had already lost the war by 1943 based purely on industrial mathematics. The captured B-17 at Rechlin answered important tactical questions for German fighter pilots. It revealed blind spots in defensive coverage. It identified vulnerable systems. It demonstrated attack profiles offering best chance of success. But it could not answer fundamental strategic question determining outcomes. How do you stop thousands of bombers when you can barely build hundreds of fighters annually? How do you defend cities against endless raids when your pilots fly until they're killed or exhausted? How do you maintain production when enemy bombs eventually find every factory? These questions had no satisfactory answers within framework of Nazi Germany's war strategy and industrial organization. The regime had started war of conquest assuming quick victory before enemies could fully mobilize economies. When that assumption proved false, when conflict became grinding contest of industrial attrition, Germany's fate was sealed by decisions made in the 1930s. The B-17 Flying Fortress, with its turbocharged engines maintaining power to 35,000 feet, represented not just tactical challenge, but strategic verdict on war's outcome. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.